black powder target practice or something. I don't know, it's really loud. But I guess hunting season's underway. Maybe they're teaching a kid to shoot. See? Crazy.
Okay, let's see, what's new? I'm still working on that podcast. It's coming along pretty well, but I'm getting derailed trying to explain the Stern Gerlach experiment. I wanted to discuss spin as it relates to magnetic fields, because the Stern Gerlach experiment measures spin using magnetic fields. I don't think people are familiar with particle magnetic dipole moments. For these kinds of general audience discussions, I want to strike the right balance of, formal versus informal. If I'm too informal, I'll be doing a disservice to everybody and to the science. And besides, it's just lazy. Informal discussions have brought about this kind of like crazy zoo of nonsensical ideas. Quantum mechanics has a long history of kind of wildly romantic ideas because people have been loose with the facts. So I'm trying to avoid that. If I'm too formal and we just kind of start with equations and go for broke, like, how does that help anybody? It's not that there's a right or a wrong way to learn something or to teach something, but I do think that context matters, and I'm pretty sure that not everybody is going to be familiar or at least get value from a deep dive right away into the discussion of representations of the three-dimensional rotation group. Although one fun fact about doing the quantum mechanics explanation using the Stern Gerlach experiments is that we can get to that at the end of chapter 1, so that's pretty cool. I kicked around a lot of ideas trying to create some kind of physical analogy for what a magnetic dipole moment would be. Things that rotate are non-inertial reference frames. They're kind of accelerating. It's a physical fact that motion of electric charges kind of generates or sources magnetic fields. And so I thought that would be one way to go about it. So I saw this crazy YouTube video of aBoat that got, that kicked out its pilot and started going around, little motorboat started going around in circles. I was thinking, well, okay, so if we think of an electron moving through space and the wake of that electric field is somehow related to the magnetic field, and if I can relate that to a boat spinning around, right, the wake is really big in the middle and kind of falls off the end, I thought, well, that might give you a sense of like rotation with a magnetic dipole moment, but the analogy doesn't really work. I would like to have some basis in truth, and so I went down into the depths of classical electrodynamics and started looking at the the various potentials sourced by moving charges, and it's a mess. It's a beautiful subject, but it's a lot of differential equations which are not probably helpful at this stage. So I went down the rabbit hole of classical electrodynamics for like a couple days, and it was fun and a lot of but that is a story for another time. So I'm still struggling, and the only thing I can think of right now that's going to help is I need to go out for a run. That usually helps clarify the mind. So let's go! Coffee.
That's just something else. Okay, so I'm back from my run, had a lot of fun. I think I've settled on how I'm going to frame this discussion of magnetic fields and spin. When we talk about particles, be they elementary particles, be they things like protons or just, atoms, silver atoms, as the case of the Stern Gerlach experiment, we're going to be talking about three separate ideas. Idea number one is going to be electric charge. Idea number two is going to be spin, and idea number three is going to be magnetic charge. I'm going to throw them out in context and show how one builds kind of upon the other. Now, I won't get into all the details now. You'll have to wait for the podcast to hear that, but I think this way that things build, it makes a lot of sense. And so this is basically how I'm going to throw it down. Electric charge is something that's pretty clear to most people. Opposite charges attract, similar charges repel. When electric charges move or spin, they tend to generate magnetic fields, right? So from electric charges and spin, we generate a magnetic dipole moment, which I think is pretty cool. The things that I'm going to try to stress is it's interesting that electric charges always come in same integral quanta amounts, plus or minus E. It's also interesting that spin comes in quantized amounts. So for stuff like matter, they always come in spin quanta of plus or minus h bar over 2. So that's also interesting. So those two interesting fundamental facts are of note. And then when you put them together, you're supposed to get something like magnetic dipole moment. That is to say, you're supposed to get some source of magnetic field, a magnetic charge, but those two things don't necessarily add up. And the most interesting example that I'm going to be able to give is the neutron, which has a magnetic dipole moment, despite the fact that it does not have an electric charge. So I think by putting these three things together in this sort of way, we can talk about quantum numbers and how things are more fundamental and kind of derived quantities like the magnetic dipole moment. But still having that relationship between spin, something that's spinning, which has an axis, and the magnetic dipole moment, which also has an axis, right? North, south points to north. And so those two things are more or less roughly related. And to be honest, like most physicists are going to relate the two of them anyway. And I think that's good enough for getting started. Wait till you see the analogy that I have set up for how we talk about setting up a beam of spinning particles. I'm super stoked on that. Anyway, yeah, I think it's great. And I'm very excited. So now it's on to, I guess, more work. So good. So good.